Right, hello. So, I promised I'd do a part 3 of the Truss questions, sort of without lengths, but I've taken a while to come up with one, so bear with me if there's like some mistakes in it, because there might be, because I did just kind of come up with this one and solve it. There are some lengths on the diagram, but the method I'm going to show you, the method of joints, I'm going to use the length to determine the angles, which I think you've already got in the question, or if you look at the accidental leaks that I put on the last video, this part 2 one that I posted last week, and I may or may not have gone through some of the angles. So, the question I've got is this one, which kind of looks like a bridge, if I can draw a bridge. Like that, and then like that. So, just a generic suspension thing. And got a roller joint at that one. And we're going to give it a triangle thing at that side. So that's all attached to the wall, and I'm going to label them because I'm going to determine them. So I've got A, B, C, D, and E. And then here we've got H, which is that one. I can't draw, but let's just go with it. G and F, because it goes that way. So on these we have loads of 30 kilonewtons, 30 kilonewtons, and 60 kilonewtons. So on that, and then the lengths, we've got 5 meters, 5 meters, 5 meters, and 4 meters, which means that because that's the same height all the way across, we should be okay. So, first thing to look at in a truss is, can we actually solve it using the methods we know? Is it statically determinate, both externally and internally? That is to say, can we actually look at them? Are there no forces acting through the different joints? Because that makes it all horribly complicated. So we've got this nice thing, so we've just got a bridge with some forces in the middle, so yes, we can solve it. There are 0 force members in the truss, so none of the members are exerting forces onto anything, so we're quite okay. So this should be quite straightforward to solve. Now, that's taken about 3-4 minutes to draw, and I'm just going to rub it straight off because, like last time, the first thing to do in any truss question is a free body diagram. So we're just going to get rid of it and simplify it. So, see in a bit, you big purple drawing. Hopefully you all had a chance to write that down before I got rid of it. So I'm going to draw it up here though. So it'll look like that, I think. Close enough. Across, up. So we've got here, we've got this, and we had 60, 30, 30. 4, 5, 5, 5, 5 of S, because I'm writing them backwards, so bear with me. And we had, I'm going to use green so you can see it. We had E here, A there, and we had, well, we will have a reaction called EY, because I think it was a roller joint, so that can only react that way, because if you push it that way, it's just going to roll off. If you stand on a ball, it doesn't move. If you push it, it does. And we had a triangle here, which means we have a reaction AX and a reaction AY. So they're all in millimeters. I'm going to be taking that way as positive if I do moments. I'm going to be taking that as positive, I think. So we should be alright. So, first thing we can figure out is it's in equilibrium. So that means we know that the sum of the forces in X sum of the forces in X, and the sum of the forces in Y equals 0. And we can make the entire problem that I've come up with off the top of my head simpler by realising that, oh, it's actually symmetrical. So it's the same thing on both sides. We've got a 60 in the middle and a 30 on either side. We've got two Y reactions. So that means that the simplest one to figure out is probably going to be sum of the forces in Y. Now, I'm sure some of you are questioning that. It's because it's symmetrical, we've got a full 120 kilonewtons reacting downwards. That's these three. Which means that because it's in equilibrium, it's not going anywhere. We know that the reaction that way, that is to say AY plus EY, has to equal 120 kilonewtons. Because it's symmetrical, we know that AY must equal EY. So they both have to be the same value. So AY must be 60 kilonewtons. Because it's symmetrical and the sum of the forces all in that direction add up and everything's fine. Right. So we've already got one of them. This one. We've got that now. And we've got that by symmetry. So, now I remember in the last two videos I said if you know what you're doing, the method of joints is easier. And I think in the portfolio question, it asks you for reactions in members, which means you know where you're looking instead of the entire system where you need to use sections. I'm going to be using, or it's better to use just the sections we want in joints. So, I'm going to use a method of joints, both because it's symmetrical, I can look at it, and that means I only have to figure out these main ones instead of the entire system. So instead of taking a full section, I can just look at the specific pieces I want. So, now that we've noted that down, I can remember it. Anyway, 60. We move on to the actual determinant. Now, this is the bit where you have to bear with me because I am just going to use the length for a minute, but you guys have the angle, so don't worry. So, if we look at joint A, and then we sort of take this out and extract it. It looks, I'm going to do that bigger. If only everything was easier to make bigger. Right. I'm going to look at that and that. We've got a reaction that way and that way. And at this point here, we've already determined that AY, which I've just rubbed off, this is 60 kilonewtons. So, that means we've got member AB, and I think I called that H. We've got AH. So B will be up here and H will be over here. So what I don't know here is theta. But I can always come back to it. It's the only thing I can't work out. Which I think you guys can, which I kind of alluded to. And the only thing I need to use the lengths for is the angles. So because I made it up and I made it really easy, it's going to be 4 and 5. So we've got, that's 4, that's 5, which means that theta will be the inverse tan of 4, that one, over 5, that one, rise over run, which is, same as last week, forgot my goddamn calculator. Is inverse tan of 4 over 5, which is 38.67, 38.7 degrees. Degrees, not radians, because it just makes the math easier for now. I worked it out in degrees, so oh well. So we now know what theta is. So I'm going to leave that up there. 38.7 degrees. No, I'm not going to lose that because it's on there. But I am going to get rid of the rest of it. Except that, because I kind of need that. But I can draw it again. If I'm good enough, I'll edit that bit out. If not, you're going to watch me draw it again. So, I probably didn't edit it, so here we go. Same thing we can do last time is some of the forces in Y and some of the forces in X. So we know some of them, which is great. So we can take the sum of the forces in Y, that one, will be this 60, because it's going that way, and I said up is positive. I should probably move that over, but I will. In fact, I'll just do it bigger over here. Sum of the forces in Y is equal to 60 kilonewtons, because this one acting that way, and we're at this point, A. And that's going to be minus whatever the X component of this is. So, no, whatever the sine component of that is. So the Y component. So we need to take sine of theta because we're going that way. So it's going to be minus AB, whatever that member force happens to be when I work it out afterwards, times the sine of our angle. So sine theta, 38.7. And we know that that has to equal 0 because it's in equilibrium. So that at A, the only member that's pushing downwards into it to give it that reaction is AB. So the Y component of this has to equal that. So therefore, we can work out that AB equals, well, it's going to be 60 divided by sine of theta, which is, I should probably write that down, 60 times 10 to the 3 newtons over sine of theta is 96,000, which is 96,047 newtons. There. Yes. So that actually simplifies down to 96.0 kilonewtons. So that's now number AB. So our number AB's reaction is 96 kilonewtons, if that makes sense. Hopefully that makes sense. If not, just drop me an email and I'll try and explain it back. So what we can determine from that is that because it's acting this way, the force is actually squishing the bar, if that makes sense. Everything's pushing onto it, it's in squish. We can determine that AB is actually in compression. So when we ask you to comment on the kind of reaction, remember that's what we mean. Is it in compression? Which is, so you've got your bar like that. Is it being squished? Or are the forces pulling it apart? And that'll be tension. So it's either in tension or compression. So they're the only things we're going to ask you to comment on. So we're going to determine that AB, this one, is in compression. Hopefully that makes sense. If not, pause it, rewind it, just kind of look over how we got to that again. But essentially, we know that all of this is equal in this direction. So we've got our 60, which has to be equal to the sine of that. So then we just rearrange that. We know theta, so we can just plug it in and get our Y force in AB. Hopefully that made sense. So, what we don't know at this point is, let's do the exact same thing again, but a little bit sideways. So, now we don't know AH. So, we can take the X reactions. So for the X reactions, what we know is, I should probably have written that down somewhere, AB equals 96 kilonewtons. I'm going to add that on there. If not, you guys remind me, drop it in a comment and I'll read it later. But I've already remembered it, so whatever. Okay, so we know that the sum of the forces in X this time also equals 0, so everything acting through this in this direction has to be nothing. So that means whatever AH is, yeah, because that's acting in this direction. It's just purely acting in this direction with an angle of 0. Whatever that is, we have to take off this 96 times by the cosine of theta this time, because we've got AB acting that way. So 96 times the cosine of theta, which has to equal 0. So therefore AH equals 96, I can put that over there, cos theta, which means that AH is times cosine of 74.96, 74,960 newtons, which I can simplify down because we're working in kilonewtons. I can simplify it down to 75.0 kilonewtons. Can you see that? That's not really a 0, it's a 6, but that's a 0. So I can now determine that AH is 75 kilonewtons. That's its member reaction, and because this one was acting that way, we know that this one is going to have its forces here, so that's going to be in tension. So that's going to be being pulled apart. And you can think about it physically, because the maths always has to give way to physics. So if I've got this, and I've got this force acting down on it, I'm actually pulling it, this is being held, this is being dragged, so you can actually think this member is going to bend like that, so it's going to be pulled. It's going to be in tension. Okay, so 75 kilonewtons tension, and we know that's AH. So AH equals compression, 75 kilonewtons tension. It's probably a better way of saving these, but whatever. So that completes that entire section. Well, that joint almost. So now we know the reactions in both these numbers. So we've got that one, which means we can move down. I think for the actual portfolio, there's only 2 or 3 joints that you actually need to analyse, but I'm going to do a fair few here, just so we really get to grips on what's actually happening. So I'm going to actually draw the diagram here this time, because that makes sense. So if we move on to joint B, which is this one. So if we start analysing this one, we're going to use a method of joints again, because we're looking at a joint. It's just straight up simpler. We can look, well, if we just draw it out like that, we've got that, and then a reaction downwards. So that'll be where B is, that'll be where C is, that'll be where H is, and that'll be back where A is. So this will be AB again, this is going to be BC, and this is going to be BH. Right. So, where do I start here? Straight up, we can change that. Actually, I'm going to make that bigger so I can write on it. No. A little bit better. Yeah, alright, so this is B. Straight up, I know I've already worked out AB, so I already know this entire ring. This entire thing is in compression, and it's 96 kilonewtons. So I already know that one. That's great. That's a fantastic start. Okay. I don't know BH, and I don't know BC, but that's fine, because, why is that fine? We know the angle, now we know the angle, must be 180 minus 38.7. Yeah? Okay, so we know that our new angle that we're working with is going to be, theta 2. Actually, no, I'll just sub it in later. Okay, we know that this angle is going to be, what is it, 51.7? No, because that's the 7, 51.3. Can you see that? Yeah. So that's going to be 51.3 degrees, because it's going to be, well, the rest of it. So we know it all adds up, and I think it was going to be 90. All the angles in a triangle add up to 180. We know this one was 38.7. That one's clearly 90. Oh, this one. So that one has to be 51.3. Okay. So let's go back to what we did again. So back to what we did before. We're going to take the sum of the forces in X first this time, because I really want to know what BC is. That has to equal 0. So how do I get to that point? Well, acting in X, we've got whatever BC happens to be. When I work it out, I don't know it yet, but whatever that happens to be, plus whatever this 96 is in the X direction. So, because we're going this way, we know that this angle is 51.3, so we need to take the sine of it, because we're not going through it, so you cut through using cosine. We're going the other way, so we're using sine, so it's going to be sine of 51.3. So we're going to take plus 96 times the sine of 51.3 degrees. So, and that should all sum up to 0, which means that BC must be, well, minus that, so 96 sine 3. Great, obviously it's going to be the opposite of that, which makes sense. That's fantastic. Not bad, considering I just came up with that. Okay, so we obviously know that that is now minus, because this is going to be a minus when we take it over there. Minus 7, well, I got 74.6 kilonewtons, but I'm going to round that up to 75 kilonewtons. Minus 75 kilonewtons. Okay, so that must mean that this is in compression. Yes. Yes, compression, because that's negative. So we're happy. We know BC is minus 75 kilonewtons, and that one's in compression. So hopefully we've understood that one. We've got that one. And again, we haven't used any lengths. We're just using the forces. The only time I use the length is to get the angles. You guys all have them. So next, anyone want to guess? Do the exact same thing we've always done. We're going to take the sum of the forces that way this time. That way. So, sum of the forces in Y. That's not even an F, is it? That's disgraceful. F. Sum of the forces F, and that has to also equal nothing. So, camera died again. Probably should get better at that one. I just managed to write an F properly. So, sum of the forces in Y equals 0. And now that looks like a G. That's not very good. So, sum of the forces in Y equals 0. Right. And we're working on joint B. So, that means, essentially, we're just adding up everything in here that could possibly have a Y component. So, we've got BH and whatever the Y component of this 96 BA is. So BH is going to be acting this way, I think, and this 96, when we come through the angle using cosine, is going to be acting that way. So we know that BH is going to be negative, so that's going to fall into minus BH, because that's going to be acting down, yeah, and that's going to be added on 96 kilonewtons times the cosine of 51.3 degrees, and that has to equal 0. So that means that 96 times the cosine of 51.3 equals BH, because I can take that from here and add it back on here. So therefore, remember BH force must equal whatever that is. So that's 96 times 10 to the 3 times the cosine of 51.3. 60. great. So pH is 60 kilonewtons. So now we know that one. So I can add that in. No, I'm going to keep alternating. That's quite cute. pH equals 60 kilonewtons, and that will be in, well, it's going to be acting that way, so it's going to be in tension because we're going to be pulling it apart. So that's going to be in tension. No, right, okay, I did that in green. There we go. Tension. Right, so we've now finished joint B. We know that, we know that, and we know that. So hopefully you guys are getting the hang of this now, without using the distances, because I think that's what was tripping up a lot of you, is not knowing where to put your distances in. You don't. That's the benefit. So last one I'm actually going to walk through. I'm just going to fly through this one, just because I don't want this video to be very long, and you guys should know how to do it. I'm going to look at joint H. So joint H is this one. It just looks like that. We've got 60 reaction there. We've got our 30. We know that's a 60 because I just wrote it down. I'm not just pulling it out of the back of my ass. We know this is 75 because that's there. And we know this, which is FG. So we don't know. No, that's a complete lie. That's GH because that one's yes. And then we'll also have this, which will be GC. So this is point H. No, I completely forgot my alphabet, haven't I? Right, so HC. Right, okay. So C's up there. This is H. GH. Downwards is 30 because it's there. Upwards is 60 because we worked it out. There, BH, and this is 75 because AH is 75. So the two we don't know, HC and GH. GH looks the most fantastic. So that's going to be the hardest to work out because we don't have this. So HC we know because it's the only thing going in Y. So we can work out some of the forces in Y, which will be equal to 0 again. Yep, that will be minus HC times sine of theta, our old theta, the one we've used, and then plus onto that our 30, which is going to be equal to 0, obviously, because it's a, yeah, so I can work that out. So that's going to be minus 30 divided by sine of that. Which is, I get 40 kilonewtons. I think that will be, because it's a truss, that will be in compression. Think about it physically. That's going to be being squished because all this is going to be compressing it downwards. So we know CH. I keep doing it. Got a pretty pattern going. So CH is 40 kilonewtons. I said that's in compression. Right. Last one. Some of the forces in X equals 0. Also equals 0. Everything equals 0 because this question's straight up. So we've got, sorry, no, that was 48. I got on my calculator. 48 kilonewtons. Yes, 48. Sorry, my bad. I just can't write numbers, which we all know because we've all been to the tutorial. I also don't know my alphabet. I'm terrible at math jokes. Sum of the forces in Fx equals 0, so we know whatever this is, this 48, whatever comes through the angle, because that's going to be the same angle, isn't it? It's going to be the same as that, because that's going to be the same as that. Plus GH, which is what we don't know, and that's also going to be added on with a 75, and that's going that way, so that's negative, so we're going to have minus 75 kilonewtons plus GH, whatever that happens to be, and that's also going to be plus 48 times the cosine of theta, and that equals 0. So shoving everything onto the other side, we can work out that GH equals 75 kilonewtons minus 48 times the cosine of theta, which means that GH equals 112.5 kilonewtons. Can you see that? Yes. 112 kilonewtons. And this beam here, which is this one, that's going to be acting that way, that's going to be acting that way. So that's going to be pulled apart because I wrote it there, which means that's in tension. So luckily that is also in purple. So that's going to be in tension. So we're going to have GH equals 112.5 kilonewtons, and that's in tension. So we've analysed all of them now. I think that's most of them. The only one we could do is point. What's the other one? We could do point G, but I'm not going to. Just to spare us all. So hopefully this process makes sense. Hopefully we've actually got that as a concept. So we're going to be, if we add this to start with, which we did because it's all in symmetry. I think that was H. And C's over there. If we have this to start with, first thing we did, separated that joint, worked out all these. Separated that joint, worked out all these. Separated that joint, worked out all these. And we already knew that one by that point because it's the same as that. We already knew that one by that point. And then the only thing we had to work out was this and this, which is that diagram there. So, hopefully that all makes sense. I think the portfolio question is a bit easier than these. I think it genuinely does look something like this if you just draw your free body diagrams properly and recognise where to use your angles. So, hopefully without using the length, that's cleared everything up. Don't forget to like, share and subscribe. Wait. No. Hopefully that's cleared everything up. I'm going to end it there. If you need any questions, then email me. I'll just try and use that Teams thing that I set up. As much as it frustrates me, it seems that you guys are helping it. Right. Thanks for watching.